Okay, I will share my screen. Is it okay?
Yeah.
Okay. Hello everyone. My name is Shu. I'm a PhD student from Berkeley, and then today I'm presenting with Mert and Shubham on SkyDiscover, which is an automated AI-driven algorithmic and system discovery. So basically, there are many recent work about like how to use this kind of discovery or sort of like evolutionary systems for like mathematical discoveries. So for example, for this is like a paper from Font Search from Google DeepMind. They're trying to advance mathematical discoveries from program search with large language model. And then last year, we've also seen Alpha Evolve, which is a coding agents for scientific and algorithmic discoveries, and some open versions of like Alpha Evolve, which is Open Evolve. JEPA, Shinkai Evolve, etc. And then recently we've seen more and more this kind of like coding agents like Cloud Code, Codex, Cursor, etc. that basically like many people are using in their codings today. So ARM-driven optimization has this like mainly two components. One component is the solution components where there's like some generators where agents generating some candidates of solutions. And the other components is the evaluator, which contains the objective functions that are returning back some scores for like the generator feedback. And in this case, many of the evolutionary system contains some sort of solution databases, which basically the generator can decide whether to search and learn from past experiences effectively from the past solutions they generate. So this kind of like paradigm have been applied to many problems like math problem, system performance optimization, code generations like kernel generation, and prompt optimization, etc. So here, there are two problems in this existing paradigm. First of all, we want to understand how to actually search for a good solution efficiently. So in this case, we have some sort of optimization space, which contains many of the past experiences and like the things they want to search for. And we want to efficiently search through this space to find a good solution. And the second problem here is that how to make sure that the solutions that you're generated are correct. So we talk about like these objective functions in the evaluator. And many of the cases, we want to ensure that the solutions that are being generated by the agents actually can satisfy all the properties in the specifications. So we designed SkyDiscover, which is a flexible framework for AI-driven discovery. And in this case, we're creating it to address these challenges. Basically, it includes modular components of like, for example, evaluations like generators, all kinds of agent architecture, and then the adaptive optimization, which will adapt the search strategies based on progress and enable AI to even evolve itself. And also, we're focusing on not just toy examples, but also real-world end-to-end system synthesis. So we have like support for these benchmarks of like math and coding, and more complicated benchmarks of like using these agents to build end-to-end system. So SkyDiscover contains of like a context builder, which contains of like how do you actually specify program context in prompt. And then the agents can be any sort of LLM calls or cloud code or codecs interacting with some environments. And then we'll have some evaluator. So the solution being generated by the agents can be like code, text, or image. And the evaluator contains some scoring functions along with some additional feedback, such as like scoring, logs, feedback, artifacts, etc. And we have some sort of like solution metadata being stored in the solution database. So there can be multiple algorithms like actually selecting from this database of like the useful insights. So this selected solutions where past experiences are used as guidance. So in this case, basically, we have like new ideas, guidance for reflections from the past experiences, which will be basically put into the prompt again for the agents to generate a better one. And I think Mert will talk about rest of the slides of like how to actually search for a good solution efficiently.
Okay, yeah, thanks, you. So picking up from where you left, what you want to come up with is like you want to come up with algorithms that search for these solutions efficiently. A problem with the previous solutions is that there's lack of adaptability in the sense that before the run starts, we need to set up the hyperparameters, and there's little chance to change these hyperparameters once the run starts. And these hyperparameters, more importantly, do not adapt to the search process. So we want to overcome this. So, for example, a lack of adaptability here is um, like this is I think from around from OpenEvolve. Initially, there is some good progress, but then it stagnates. And in the like manuals when we go, they suggest that actually around iteration 50 or like after one run ends, we need to start another run with another set of hyperparameters. So this is because of these fixed strategies. But even Cloud Code can quickly stagnate because it does not have these adapting parameters. So we have two algorithms. The first one is AutoEvol. AutoEvol, basically the idea is how do we adapt the search hyperparameters based on the progress of evolution. And EvoX, um, the idea is how can we come up with a meta evolution that where the algo AI optimizes the search process, searching for solutions itself. So yes, the first thing is Agarwal. In Agarwal, the essentially inspiration is like Adagrad and Adam algorithms. That's where the name comes from. In continuous optimization, this is sort of like a solved problem. You would have different learning rates based on the progress of different parameters in your gradient descent updates. Um, so in of course, zeroth order optimization, this is not super clear, but we came up with three different adaptation stages, local, global, and meta. At local, the idea is, okay, you have a population of programs. How do can you adaptively decide whether you should explore or exploit? In global adaptation, the idea is um, we chunk different solution that are discovered in the past into different populations that are isolated from each other, that are called islands. And the idea is can we dynamically spawn new islands as the old ones stagnate? And can we adaptively select new islands using some multi-arm bandit score? And then the last part is meta guidance, where the idea is, okay, maybe we need to again change or tune the tactics um, based on the progress of evolution. Yeah, you can look at the paper using the QR code. Yeah. The second is EvoX, where the idea is like meta evolution. In EvoX, we want to ask even like a bigger question. Um, can we not impose any particular search strategy? And can we have another loop that optimizes this search strategy itself? So um, the decision to store past solutions and sample them in EvoX, AI optimizes that part as well. So in the architecture, basically there's a bottom loop. The bottom loop is the classical like evolve loop, where the goal is to evolve a strategy, evolve some solution, uh, such as maybe like circle packing or some signal processing solutions. But then the key innovation is we have another loop sitting at the top. This part basically tries to find a good search strategy for the bottom loop, such that good solutions might be discovered. And what triggers the top loop for generating new search strategies is essentially stagnation from the lower half. And thanks to the stagnation, EvoX stays very efficient in terms of compute and token. Um, you can also look at the EvoX paper from the QR code on the right hand side. And yes, the results are very um, affirmative. Like in math tasks, EvoX and AdaEvol almost always outperform other open source model methods, while outperforming AlphaEvol usually. And the same thing goes for system optimization tasks such as expert parallelism load balancing or um, like transactions on databases, etc. And yeah, similarly on compared to programming problems on Frontier CS, Agarwal and UX are pretty good compared to other open source methods. Yes, and now Shubham is going to talk about uh, the next steps for the SkyDiscover project that we did.
Hi everyone. I think we are short on time, so I'll try to quickly touch upon these two things. So all that we saw till now were more like benchmarks, but we wanted to push it a little bit towards real world problems, and there we started thinking about what we know. So we generally come from a system development background, system building background. So we started with the problem of key value store. It being a very simple API, yet the design space is pretty big. So we can keep moving the slides so that we are on time. So the problem was that of course we wanted to build bespoke systems that, okay, say you have a requirement, you want a workload that your system works perfect on. You just want to build a system from scratch altogether. And there we used SkyDiscover sort of loop, but it was basically more agentic in terms of using Claude code, but not really using LLM. And then it takes care of all the three things: the environment it is going to work on, the workload that it wants to over optimize for, and the requirements of the system. Now, next slide, please. Yeah, the challenges that of course come in this problem was that if you have a particular workload, it tries to overfit to that distribution, which makes building systems hard. And the second challenge being that you can see that there are a lot of reward hacking problems, that it might not store things properly. So when we have a optimization pressure that, okay, we want to optimize our system for a workload, the correctness comes to some sort of less shackle kind of place. Yeah. So we did two approaches here. The first one was a test-driven approach. The test-driven approach is more like you have an auditor or some sort of an agent that is trying to break your system, while the main SkyDiscover loop is trying to build the system. So that's how the evaluator and the main coder agent looks like. And it's more like you try to come up with the requirements as a requirement doc, and then the system keeps on getting built. But the agent is trying to break the system at the same time, and it tries to keep on adding more and more specs, trying to figure out those holes, and hence it is able to do it. The second approach that we took was using proofs. So all these literature on writing systems and then proving it to be certified requires you to use some sort of lean kind of language. So there we came up with a paradigm which was more like inductive deductive synthesis. And in that one, the way we do it is we build the system and we write the proof at the same time. So the system and the proof acts like closed loop, where whatever you are not able to prove is basically a whole, and then the agent has to figure out how to exactly write it or change the implementation so that it can be proved. Now, what proof mean is in this case is more like different protocols. For example, if you want a system that has some sort of consistency, that okay, you need to read before write or things like that, you have to prove that okay, for any workload or any kind of concurrency condition, it is actually behaving that way. So these are the two things. Maybe we want to wrap up. So uh, I'll quickly, like, we will quickly go over the design. That this is the overall idea of the first one, where you have a coder and an auditor. And for this one, of course, the next slide has a lot of results where we were able to beat a SOTA key value store, which was faster from Microsoft, and we were able to beat it per workload basis. So every workload, we are building a new system which is optimized for that, and it can behave better than any existing system that was more generalized. And the second one that I talked about was the correctness one, where the main challenge was the amount of time it takes for building system, but still it remains more like a toy system. But in our case, of course, agents were able to do it in like a couple of tens of hours. And the system main idea was synthesize the code and try to prove it. This is some sort of a take against vibe coding, that okay, you can't really vibe code large scale systems. You can vibe code very simple algorithms. And this is something that we are very excited on, that okay, building systems from scratch or making systems bespoke to you can have a synergy of test driven things and proof things, and we are now working actively on how do we integrate both sides to make systems bespoke. So these are the things, and of course we were able to build a system that was completely proven and was able to beat a previous formally proven system by about 3 times the throughput. And in terms of human time, it was literally 200 times faster because the agents parallelly were running and trying to figure out different parts of the proof. Yeah. So that's more or less our summary. And we are very excited about exploring more into the space of systems research now, that even if we talk about, say, inference engines or training frameworks and things like that, how do we make things which are more tuned for specific requirements and workload, and how do we make agents go from benchmarks to real world settings? Yeah, thank you.
Thank you very Oh, 1 second. Let me turn on my screen. Okay, thank you very much, guys. It was really nice talk. I think we have time for a few questions. I actually have some of my own. I don't see any on the chat right now. So basically 2 questions that come out of my experience working with some of these agents. So first of all, did you guys also test SkyDiscover with like cheaper LLMs or open source models like Qwen or like smaller ones just to control for the power, how powerful some of these frontier models are? And the second question is, did you also do some ablations regarding like the many components of your framework?
Yeah, maybe I can take that. So we do actually have a lot of results on open source models now in the paper. So it's at the end of the paper. You can take a look. Our observation was, of course, it was not able to beat SOTA models, but if you compare it against how open source model was doing versus how it was doing with the EvoX or Ada Evolve as the scaffold, it was pretty big of a jump, and the jump was even high because the agents in general were not able to figure out properly because of their lack of RL training. But our framework, because of the way it was orchestrating the search, it was doing pretty well. And there was some scaling behaviors that, okay, if you let it run, maybe at the same cost that you are spending on a Claude machine, you might actually get very good solutions from your Qwen running on a VLLM. And for the ablation, yeah, very good question. It's a little hard for this kind of problem to do ablations because of the randomness involved. Like even run-to-run randomness is a very big challenge. But we did try our best to do multiple ablations and average around for like 3 to 5 runs. Some, of course, our design was also evolved based on those experimental ablations, but in the paper, we again try to provide a very exhaustive list of different components, how things are working, which parts are the biggest contributor for all the 4 works that we presented.
Okay, very nice. Thank you. Just a couple more questions from the chat. There's one from Daniel. Can you frame EvoX as a reinforcement learning procedure? And if so, what are going to be the states, the actions, and the rewards?
Yeah, that's a good question. Shu, you want to take that or should I go on?
Yeah, so I think probably you can actually frame it as like a reinforcement learning. Then the state would be we actually condition it the search strategy generations by the current like optimization or search state, which is mainly the downstream solution population, and also like a summary for like what kind of downstream solution population looks like. Then the action would be like the search strategy being chosen or actually like generated by like this meta level policy. Um, and probably like the reward that we actually designed for that case is that during this window, like for when you actually apply this search strategy, how like what is the downstream like improvement of these basically like whether you can generate like a better solution within this window. Yeah, so we have like more detailed scoring functions of like how we evaluate whether like this each of the search strategy is good or not in the paper.
Okay, thank you. And just a final question, maybe from Nigella. How do you design an evaluator to be resistant to reward hacking? Do you use adversarial validation as an additional test set that is not visible during optimization or something else?
Yeah, so for the last 2 works, this is what we exactly focus on. So for the first one, there is a adversarial agent which is not visible in the start, but as and when the agent is trying to build a system, the adversarial tries to find those holes and keeps on adding those tests. Or if there are any assumptions or changes in the requirement that you started with, for example, the intent of the system designer was not clear, and there are some things that the agent is trying to figure out if the intent should have been this sort. And the IDS work, you don't really care about it because you are trying to prove it. So that's where we say that, okay, using a proof assistant can actually let you not try to find more and more test cases because tests are always going to be in some way incomplete. But of course, the Jitski paper takes the stand because a lot of the systems that we actually, that's why we try doing both approaches. But yeah, great question again.
Okay, so we actually have time for 2 more questions. I'm going to say them both at the same time so you guys can maybe subdivide them. The first one is from Hosperus. Did you try crossing the meta improvements across self-improving meta agents? So maybe crossing both of the approaches, EvoX and Evolve. And the second one by Henry Robbins. Any reason you choose ROCQ instead of Lean for the proof assistant?
Yeah, so of course, for the first one, we have a good result, which actually shows that if you start from ADA Evolve, it gives you a very good jump because it's a very, very well designed algorithm. And then EvoX can still make it more scale in terms of changing some things within the ADA Evolve algorithm to give you even better results. So that is how you can start from anything, and then you can still use EvoX to optimize it to the best extent and make it particular to your problem. So yes to that. And ROG instead of lean, in the paper we show that we can work across both the baseline systems, and more or less most of the KV store kind of systems used to use used to use ROG because it was more popular at that time. And lean is something that has come more recently with the math stuff. We are trying to actively see if the entire system can be built in lean also, because again we have ablations showing that it is cross language, IDS is cross language compatible, so hopefully it is. But yeah, I mean that was the only decision it was there. And there was one more question about using Claude Code as a model in SkyDiscover. So that is something I would like to give a shout out, that we do support Claude Code in SkyDiscover. So there is a search mode known as Claude Code. If you just use it, it's more like a secure way to use Claude Code for the entire harness, and then you can actually see for a given budget, you record everything very properly in a Docker, and you can actually run Cloud Code for your problem and actually do a apples to apples comparison for that.
Okay, great. Thank you guys very much again for the presentation. It was really nice. And now we're going to be in our breakout sessions really soon.